Cool. So what you have here in front of you is the oscilloscope, and it's basically just a very sophisticated voltmeter. So if you remember back to electricity last year, we could measure voltages using those funny little devices that came with your electronics kits. This is just a really, really expensive scaled up version of a voltmeter. And literally the only thing it does is it measures voltages. So it takes voltage and it plots it on the y-axis, and it plots the voltage against time. So the reason you're seeing nothing on the screen is because there's no input. So that straight line you're seeing there is just the trace moving left to right. But what I can do is I can slow that trace down. And you can see there I've slowed it down quite a bit. If you watch the video later on YouTube, you'll see this is like whizzing by like a little dot. Ooh, and then I can also speed it up so that it basically looks like a continuous line. Ooh, so I have control over the time setting. That's the one on the right-hand side over here. And then the other one that you're not going to see so obvious is I have control over the voltage setting, and that's going to be the vertical up and down displacement. So unfortunately, I don't have anything to measure at the moment because I don't have a source of waves, for example. I don't have a microphone, so I can't even measure sound waves. But what you can see is that I can actually play with this thing. And if I touch one of the controls, if I do that, you can see a wave forming there. Let's see, do you see that? Yes, sort of. It's a bit laggy, but essentially you should see a bit of a trace going on there. And in the horizontal direction, it's a time base. And then in the vertical direction, it's a voltage base. But I can play around with that base, and I can change the input setting, so I can actually play around. But the input wave is exactly the same. I'm just drawing it differently. In other words, the frequency hasn't changed. It's just the way that I changed the time base that makes a difference. Cool, so it's very useful. When you guys get back to class, we'll do a couple of demonstrations. I'll get a microphone and I'll hook it up, and then we can calculate, for example, the frequency of a sound wave. But for now, just trust me that it's a real life device. It's not just something you're going to see in the textbook, for example. Cool. Any questions? Everybody good? Good. Okay, so it used to be in the IGCSE syllabus. They took it out, and thank goodness, because it is quite confusing. But when I say confusing, I don't mean difficult. I just mean that it requires a little bit of extra thought. It's not as straightforward as just reading a graph, for example. So what I'm going to do is I'm going to set the page with a sort of a grid reference in the background. And this grid reference here is basically going to be the trace on my oscilloscope. And then I'm going to show you what it means. Okay, so an oscilloscope technically doesn't have an X and Y axis. What you really just have is a vertical displacement and a horizontal displacement. So we're just going to make an imaginary box, and we can imagine that's the screen of the oscilloscope. So it's nothing in particular. And then we're going to see that. And then we're going to define the X and Y blocks. So what does each X and Y mean? So if I say, for example, in this case, I can give this, let's say 5 millivolts per block. So it's like reading a graph paper, meaning that every time I scale, every time I go up or down a block, I'm going up 5 millivolts. Cool, so that would apply everywhere on the y-axis. It would be 5 millivolts. Remember, it's not an X and Y grid, so you don't have a 0, 0 point. There's no origin on this graph. Cool, and then what's very nice about this is that I can also play with the time axis, and I can give it, I can play around with the time axis and I can change this. So let's say, for example, I make this one, let's make an easy one, for example, 2 seconds. So each horizontal displacement is 2 seconds, and you can draw that anywhere. So it's like reading a graph paper, essentially. Well, then what's going to happen is that you're going to get a trace. You're going to get some kind of signal happening on the graph. It could be a sound wave. It could be an electrical signal from a generator. It could be anything. You can actually monitor chemical reactions like this. It's a long story, but it's amazing. Cool. And then essentially what you're going to find is you're going to see somewhere in that page, you're going to see a graph forming like that. not a graph, sorry, a wave forming. Cool. Let's just assume that carries on a little bit on that side, and then it just tapers off over there. Cool. Then what you've got to do is you've got to use your sort of reference points, and you can calculate the period now for the wave. So we can calculate the period of this wave. We can say, okay, if that's the start of the wavelength, that's the end of the wavelength, then it spans approximately that many blocks. So I know it's a bit difficult to see here, but we can assume that this is approximately a half, and we can assume that that's approximately a half. In real life, it's not going to lie directly on the lines. You're going to have to either estimate or count multiple waves and then sort of make a estimate. Ooh, and then that's one full block, that's one full block, one full block. So we can say here that one wave is equal to 4 divisions. Ooh, when I say divisions, I mean horizontal blocks. Cool. But then we can say, what is one division? So we can make a link, and we can say, well, I know that one division is 2 seconds. So in other words, I can substitute in there, and I can say that one wave is equal to 4 times 2 seconds, which is equal to 8 seconds. In other words, the period of the wave. So what I've calculated there is, let's call that capital T for period. Cool, everyone happy so far? Any questions? No, Kamaz is good. Mumbai is good. Everybody's good. And then what's very useful about this is now that I have the period, I can calculate the frequency. So if you remember the equation, I can use the equation frequency. You're not going to be able to see the green. Let's write with a better color. Let's just stick with red. Ooh, we can calculate the frequency, and the frequency is 1 over t, which is equal to 1 over 8 seconds. 1 divided by 8 is 0.125, and that'll be in hertz. Cool, so the frequency of this wave is 0.125 hertz based on my time-based setting. Cool, any questions so far? No, we're good. We don't need to know the speed of the wave. If we wanted to, we could calculate the speed of the wave if we knew the wavelength. In this case, this is not the wavelength, it's the period, because on your horizontal axis, it's time, not distance. Cool, so this is not the wavelength, this is the period. Okay, so that's one example. Let's do another example. I'm not going to draw the block anymore, so I'm not going to draw the face of the oscilloscope, but I will give you the time division. So now is a good time to have a piece of paper and a pen out so that you can do this example. Okay, so anybody just shout out, what would you like your horizontal time base to be? What number would you like to give it?
4.
Pardon, say that again.
4.
4, good, good, good. And let's make it seconds for now so we don't get too confused. So in other words, each individual block is 4 seconds. And this is literally a setting on the oscilloscope. You can change your division to 4 seconds per division. Cool. Then you just draw a wave. So you draw some kind of wave, and it's difficult to draw sine waves, but you draw some kind of wave. And then the question could ask you something like calculate the frequency of the wave. Well, in this case, you can just estimate. I'm saying in this case, we're not going to get it exactly perfect. So let's assume that that's exactly halfway between those 2 blocks. And this one works out perfectly onto that block. Cool. So the question now is, can you calculate t, the period of the wave, and can you calculate f, the frequency of the wave? Cool. I'm going to pause the video. I'm going to give you a minute, minute and a half, 2 minutes, calculate the period and calculate the frequency of the wave. Okay, so who wants to work me through it step by step? What do you want to do? How do you solve this problem? Anybody, just one of you, just to decide. Mumbai, Angelica, Stefan, someone. Kamaz. Yeah, Kamaz, go for it.
So you add up all the blocks to get the period.
Cool. So did you count this as a half?
Yes.
Ooh, and then you said that's 1, that's 1, that's 1, that's 1. So you said how many blocks?
That's 4.5 blocks.
4.5, correct. And then what did you do with that?
You times it by 4 seconds.
Correct, 4 seconds per block. And that will give you your answer. So I've got a little bit of space issues here. 9 times 2 is 18, am I correct?
Isn't it?
I don't know, sorry. Wait, 4.5 times 2 is 9, and then times 2 again is 18.
Yeah, it's 18.
I could be wrong.
Oh.
I don't know. I'm doing it in my head. I don't have a calculator.
Yeah, it's 18
It's 18. Okay.
on the
So,
calculator.
Yeah.
good. And then the frequency commerce, that's pretty straightforward now that you have the period.
Yeah, it's just 1 over 18 then.
1 over 18, and that'll give you in hertz. In physical science, when I say physical science, physics and chemistry, you have to give it in decimal form. So you have to give this to whatever this is in decimal places. And then obviously count your significant figures and round off accordingly. So no fractions in physics or chemistry for that matter. Cool. So everyone get the hang of that now. Everyone happy with the basic idea? We count the blocks, and then we work out the period, and then we can work out the frequency. Cool. So let's look at a slightly more. Let's make it a bit more difficult. And what can you change on the horizontal time axis that's going to make it one step harder to calculate the frequency in hertz or the period in seconds? What can I use instead of using just regular good old-fashioned seconds?
Using milliseconds.
Minutes?
Yeah, minutes would be interesting. Minutes would be very complicated because then you'd have to convert minutes to seconds. But if you think just SI units, milli or micro or something, cool. So give me a number and then a prefix and a second. So any time-based setting in not just regular seconds.
5 milliseconds.
5 milliseconds, okay, so we want 5 ms. And this is literally a function on the oscilloscope. You can set to 5 milliseconds, it is possible. Ooh, and then you draw your wave. I'm going to try and draw it a little bit differently this time so that it's a bit more challenging. Ooh, something like that. And then the question's exactly the same, so nothing different, but they want the period. And that can be in milliseconds, that's fine. You don't have to convert that. But when you calculate the frequency and you want it in hertz, it means you must first convert milliseconds to regular seconds. Ooh, so you've got to convert first. You can give the answer for the period in milliseconds, but in order to get hertz, you're going to need to convert to seconds. Okay, so I know you probably can't draw on your screen there, so I'm going to give you a bit of help. So now, because we have so many waves, instead of just trying to find the wavelength of one wave, we can kind of try 2 wavelengths. Let's see here. If we take that point and we take that point, would you agree with me that this tiny portion here is approximately equal to that tiny portion there? Yeah, so that's good. Then we can calculate the distance between those points. Oopsie, let's make you a straight line. Cool, straight line between those points, and that's going to be equal to 2 waves. Sorry, can you see the green? I apologize, the green might not come out so nicely.
Yep.
Green is good? Okay, excellent. Okay, so same question. Calculate the period in milliseconds, and then convert it to seconds to work out the frequency. And just remember that I've given you 2 waves. I haven't given you 1 wave.
So is that like a
Okay, who wants to talk me through this one?
I would like to.
Yeah, sorry, whoever
Gloria.
said that first. I don't know who it was.
Gloria's hand was up.
Yeah, Gloria, go for it. So then by then you can do the next one if you want. Okay, so talk me through it, Gloria.
So this is 4 waves.
4. Oh, so you counted the entire 4. You didn't use the green line that I gave you.
No, yeah, no, I used the green. I'm not, this is not 4 waves, sorry, 4 blocks.
4 blocks, correct. Are you sure it's 4 and not 3? Yes, it's 4 blocks, correct. So 4 blocks, yes.
4 blocks. and then times 5 milliseconds.
Times 5 milliseconds, correct, gives you
20
correct.
for
Milliseconds,
the period
correct.
for 2 waves.
For 2 waves
And then you divide
equals
it.
2t, correct.
Yes,
So that
and then you
means t
divide it by
equals
2. Then you
perfect.
get 10 milliseconds as the period,
Correct.
and then the speed will be 1 over 1000 because it's in.
Careful. So we want to convert to seconds. Are you going to multiply by 1,000 or divide by 1,000?
You're gonna multiply by 1,000.
Well, in this case, you've got the
Divide.
divide, correct. So what you're going to do is you're going to say
Yeah.
that you have 10 milliseconds, and then you're going to divide it by 1,000 to get 0.01 seconds.
Mhm.
So what you did is you thought of the kilo. If you had kiloseconds, then you would times by 1,000. But because you have milliseconds, you're going to divide by 1,000. And then you can calculate the frequency based on that. What's the 0.01? Am I right at 0.01 or did I do that wrong? It's good.
No, you're good.
That's good. And then the frequency there is just 1 over 0.01, which I'm guessing is 100. Yeah, 100,
Yes.
everyone good? Good, good. So the frequency is 100 hertz. Now the interesting thing is if you convert, if you didn't convert, you wouldn't have gotten millihertz, you would have actually got kilohertz. And I'll leave you to think about why that is. So what is milli in the seconds sense would become 1,000 times bigger in the hertz sense. So it'll actually become kilohertz if you didn't convert. So I'll let you think about that and go for it. Okay, so these are pretty basic questions. These are pretty straightforward. But what they can also do is they can give you the frequency of the wave or the period of the wave. And then they can ask you to calculate the time base. So it's like asking the question backwards. So this is quite a tricky one. So let us think. Based on that frequency, it was 100 hertz. Okay, so I'm going to give you a question that starts like this. And I'm going to tell you that the frequency of the wave is equal to 400 hertz. So that's given. You don't have to work out the frequency. But from the frequency, obviously, you can calculate the period. And then they'll give you a graph like this or an oscilloscope picture. So a couple of waves, couple of waves, couple of waves. Do we have anything that lines up nicely? No, let's throw another one that maybe. No, also not. Let's see if we can get a better one. So I'm just going to make it easy for you so that you don't have to guess too much. There we go. So let's just assume that that's one wave. Let's just assume it's half-half. Yeah, so exactly halfway. And then the question is, this is an interesting one. They're going to put the question mark over here. What is the time base setting on the oscilloscope? So in other words, what is the seconds per division? So calculate the seconds per block. Calculate seconds per block. And I'm not going to say it's easy and I'm not going to say it's difficult, but all I'm going to say is you're reverse engineering the question. You're working backwards. Cool. So you're going to do exactly the same thing, but you're going to do it backwards. Cool. Any questions before you start? No? Good. Okay. I'm going to pause, give you 2 or 3 minutes.